All right, so today we want to go back and review what the graph of the exponential function looked like. If you remember, it was a curve, and it was a curve that had a boundary. We had this asymptote, uh, that imaginary line. We always said it was like a dashed line because it's not really part of the graph, but it is a boundary of the graph, so that's the asymptote. It also had a pivot point, the point where it changed from being like a gradual curve to being a very steep curve. Um, and then we also had the curve itself. Um, in this case, this one is, if you recall, growth was going up. And anytime that the base is a number that is bigger than 1, then it's going to be growth. If you notice, if we change this number, make it 3, the pivot point and the asymptote don't change. I could make it 10. Pivot point and the asymptote don't change. These are the standard locations for all exponentials. All exponentials have an asymptote and a pivot point, and they don't change based on whether it's growth or even if it's decay. Let's take a look. We said if the number was between 0 and 1, a small fraction, that's how we got exponential decay. So let's see what it looks like if we do 1/2. Pivot point, still 0, 1. Asymptote, still right here on the x-axis. Any fraction, I could do 1/10. All right. What you do notice is when we change those numbers, the curves themselves become steeper or less steep. That's what that number actually controls, but it is still decay. And that decay still has to go through that pivot point and that asymptote. And that's what we're noticing with all of the exponentials. All exponentials have this graph. So it's very important for us. And as we go through, and when you come back after spring break also, you're going to notice that all functions have the same shapes. We learned this with quadratics. They were all parabolas. No matter where on the graph we graphed a parabola, it was going to follow that same pattern. So if we knew where the vertex was, we could draw that graph because all parabolas had that same graph. All exponentials have the same graph. And so I can graph all exponentials as long as I know where it's starting from. I know that all exponentials have an asymptote at the axis and a pivot point that is 1 above the axis on the y-axis. That doesn't change no matter which exponential I'm dealing with. I can change these numbers all day. These numbers over here for the base, and I'm still going to have a pivot point 1 above the asymptote on the y-axis. And that's always the case. At the beginning of Math 2, we discussed how you can transform functions. We learned how to move functions on the graph. We can move this exponential function around on the graph. We can stretch it. We can translate it. We can reflect it. All of those things we can do, all those transformations, if we remember what our rules were for transforming. So if you remember, to move something up and down, or to move something left and right, to translate, we translated by adding or subtracting. And the direction that it translated depended on whether we added inside the function or we added outside the function. We said outside the function moved things up and down, and inside the function moved things left to right. So if we think about that in context to our exponential function, we have to know where's inside and where's outside. So inside the exponential function would be in the exponent. Outside the exponential function would be outside the exponent, over to the side. So moving this graph up and down, let's think about what would actually change. Moving up and down would affect this asymptote. If I moved it up and down, it wouldn't be on the axis anymore. Moving it left to right doesn't really change anything because it's a horizontal line. So moving it left to right wouldn't change it much, but moving it up and down would. Moving the pivot point up and down, it's still 1 space above the asymptote. That doesn't really change. You know, wherever the asymptote is, the asymptote gets moved, and then the pivot point is just going to be 1 above that, wherever it is. But moving it left to right does actually have an effect on it because it wouldn't be on that y-axis anymore. It's still going to be 1 above the asymptote. It would just move left to right. So that means that inside the function up here is going to affect the pivot point. It's going to move it on or off of the axis. Adding something out here is going to move our asymptote. So let's take a look. let's say I wanted the asymptote, instead of the asymptote being at 0, let's say I wanted the asymptote to be at 3. I want to move the asymptote up here. How would I do that to this function? So for this function, if I wanted to move it up 3, I would have to add 3. And look at that. By adding 3, the asymptote is in fact now up here at 3, and my pivot point is still 1 above it. 1 above it, no change there. It stayed 1 above it. Pivot point is always 1 above it unless we do something to change that. But if we're just moving it around up, down, left, and right, it's going to be 1 above the asymptote. So let's say I want my asymptote to be back at 0, then I just don't add anything to it. If I wanted my pivot point, though, let's look at this pivot point here for a second. If I wanted my pivot point, instead of being here on the y-axis, let's say I wanted it to move over to, nope. Let's say we wanted to move it over to 4. There we go. I want it to move over 4 spaces. Maybe over here. It's still 1 above the asymptote, but I want it to move to the right 4 spaces. If you remember, when we did those function transformations, inside the function was a little backwards. Adding actually moved it to the left, and subtracting actually moved it to the right. So if I want this to move to the right 4 spaces, I would have to subtract. Ooh, not outside the function, but inside the function. I think that's going to require some parentheses on my part. There we go. And look, it did in fact move it. We've got it moved by subtracting 4 inside the function up in the exponent. We have now moved this over 4 spaces. So the reason we learned those transformations at the beginning is that as long as you know what the building blocks for a function are, in this case, the building blocks for an exponential function are the asymptote, the pivot point, and the curve. If you know what those building blocks are and you know where their default position is, we can move them all over the graph and not have to relearn how to graph every single graph. All of them move in the same ways. By adding inside, I move it left to right. By adding outside, I move it up and down. One of the other transformations that we talked about was stretching. We can stretch. We can stretch these graphs. We stretch our parabolas. Remember, when we multiplied by a number outside, we had to stretch what we went up by a vertical stretch on our parabolas. We can do that for an exponential as well. If I'm stretching the exponential, what I'm doing is I'm increasing this gap. We said that the pivot point was always 1 above the asymptote, and it is, unless we multiply by something to stretch it. We can stretch it. So if I want that pivot point to be further away from the asymptote, let's say I want it to be up here. I want there to be 3 spaces between the asymptote and the pivot point. If I want that to happen, I would have to multiply outside the function by 3. If we multiply, that stretches it. And so now my pivot point is up here. And I can see that it moved, instead of being 1 above the asymptote, now it is 3 above the asymptote. That works too, even if it's fractions. Let's say I wanted it to be not even a whole, I didn't want it to even be 1 space above, I just wanted it to be half above the asymptote. You know, that would be squishing it. So instead of stretching it, I squished it down. I squished it closer to the asymptote. All of those stretching and squishing comes from multiplying. So this number here can tell us how far away from the asymptote our pivot point is. We also learned that you can reflect. Let's say I don't actually want my my exponential to be going up. I want it to be going down over here. We did learn that if I want to reflect this or reflect anything over the x-axis, we just have to multiply it by negative. So now notice, instead of the pivot point being 1 above, the pivot point is now 1 below. And instead of going up, it is reflected, and now it is going down. So all of those transformations apply to every single function. And so if we know these building blocks, that we have an asymptote on the axis, a pivot point on the y-axis that's 1 above the asymptote, and that if the number is bigger than 1, the curve goes up, and if it's less than 1, it goes down, I can graph any exponential function by transforming it and moving it around the graph. And so this is how we use transformations to help us learn how to graph functions.